much. So this is the 10th session of the part 1 of a series of lectures on non-stationary time series analysis with modern signal processing techniques. So last time, we talked about the D-shape algorithm, and here is the MATLAB code, which you can find online. And today, we will focus on the applications of D-shape algorithm. I'll give you some applications that you can see why D-shape can be helpful. So the first application will be the transabdominal maternal ECG. Okay, there are several papers, applying D-shape algorithm to handle the transabdominal maternal ECG, which you can find online. So this is a very quick recall of fetal ECG. Okay, so I'll just quickly show you. This is the ECG signal that you can record from maternal pregnant woman's abdomen, and there will be some small spikes that are associated with fetal ECG. The question will be how to decompose this signal into two pieces, so that one piece is maternal ECG, the second piece will be fetal ECG, and that is actually a long journey to achieve the goal. So first, the application of the D-shape algorithm in this kind of signal. So this is the ECG signal, transabdominal maternal ECG signal, and this is what I have shown you before, the spectrogram. As you can see, there are several nice many curves, but it is not very easy to identify which is which. But if you run the D-shape algorithm, that is what you get. You see there are very clearly two curves, right? One and the two curves. And these two curves are associated with what? This slower one is the maternal heart rate. This higher one is fetal heart rate. How can I say so? Because we have the ground truths. We have a simultaneously recorded fetal ECG. So we have ground truths, and they match very well. So you get the instantaneous heart rate of the fetal ECG. And to our knowledge, actually, this kind of algorithm will give us the state-of-the-art result for fetal heart rate estimation. Well, if you only have only one channel, at least up to 2021, 2022, it was the state-of-the-art. Today, 2024, I don't know, maybe that's been a better algorithm, but well. And this is another example, which you can see is more kind of crazier and whatever. This is the spectrogram. What is interesting in this spectrogram is, you see, in the low frequency region, it is weaker. In the high frequency region, it is stronger. And if you pay attention to the signal, it is kind of more like the derivative of delta major. So that in the frequency domain, the low frequency is weaker, and high frequency region is stronger. That is how it looks like. Okay, and again, it is very difficult to say what's going on, where is where, what is what. But if you run D-shape, you get two curves. And here, the frequency is from 0 to roughly 10, and I zoom in to show you 0 to 4, so that you can see a clear picture, two components. Again, the low frequency component is for maternal ECG, for maternal heart rate, and the higher frequency is for fetal heart rate. Why so? Because we have ground truths. Okay, so that is kind of the result you can get. Now, the fundamental question to ask is, now you have the heart rate, then can we get to the maternal R peaks? What are R peaks? A quick recall is this spike, the peak, the maximal, local maximal peak, that is the R peak. And as I told you, we can read that this fatter one, whiter one, this is maternal ECG, this is maternal ECG, but this shorter one or narrower one, this is fetal ECG. So we want to determine these peaks. We want to find all these peaks. That is our goal. But how to convert from the fetal heart rate or maternal heart rate to the R peaks? Once you get R peaks, then you can determine heart rate. But how to reversely determine R peaks from the heart rate? And you may say intuitively it's easy, right? Hey, come on, they are just spikes. We can easily do some truncation or something. But turns out though it's not true. For example, here the fetal heart rate and maternal heart rate, they have similar height, so a simple thresholding may not work. And the traditional commonly used double kernel techniques may also not work very well. And this is short time Fourier transform, which is not very well. It's difficult to say too much. So what we can do is we can first get maternal instantaneous heart rate by the shape synchro squeezing. Okay, once we get maternal heart rate, then we can just apply some dynamical programming to solve this minimization problem, so that we can get maternal R peaks. So what we do is we assume the maternal R peaks locations are called BI, and there are capital M, small m bits. Okay, that's our assumption. And then we can use the instantaneous heart rate we can determine from the D-shape algorithm. And this D-shape algorithm, you can use it as the hinge point. That delta M at BI will be the instantaneous heart rate at time BI. And then when you use the two consecutive heartbeats difference divided by frequency, then hopefully, ideally, they should be as close as possible to 1. Ideally, they should be as close as possible to 1 if we find the R peaks correctly. If it is very, very close to 1, then you can imagine this guy would be 0, right? So you take square, make it positive, and you say, hey, this guy should be anyways kind of regularized if everything is good. This one should be very, very small, and when everything is good. And now you put some penalty term in front. Then you solve this optimization problem. You get the maternal R peaks. Then you can say, hey, we can apply the same procedure to get fetal R peaks, right? Because you have fetal R peaks, fetal heart rate, and so on. But in practice, this may not work very well. The main reason is for this kind of signal, actually, usually the fetal heartbeat, fetal ECG is weaker. So if you have the maternal ECG there, this algorithm may be deviated by maternal ECG. So the performance is not good. You can do it, but the performance is not very good. Okay, so what we need to do is first we get maternal ECG. We get maternal heart rate, we get maternal R peaks, and then we achieve the decomposition. And how to achieve the decomposition, that will be the topic in the second part 2 of this series of lectures, where these manifold learning algorithms will come into play, and we will skip this part today. And once you achieve the decomposition, then you get to the fetal ECG, and you run the same optimization process again to get fetal R peaks. So this is an example of decomposition and obtain fetal R peaks. So this is the transubdominal maternal ECG. Suppose you apply the algorithm I mentioned, which I mentioned, but I haven't given you details about decomposition that we will discuss in part 2. That will be the fetal ECG you obtain. And you see, this magnitude is 20, this is 5. And now I can superimpose this signal over the transubdominal maternal ECG. So it seems to fit reasonably well. And then you can run the dynamical programming to detect the fetal R peaks. And once you get our fetal R peaks, the mission is not yet done. We have to proceed to do some other things, but that is the current result up to now to get fetal R peaks. And these crosses, they are ground truths. So we want to quantify how good we can detect fetal R peaks, and so that we can see how well the algorithm performs. So what we can do is, this is the fetal, this is the ECG signal, and the red circles, they are the estimation of the fetal R peak. And by our eyes, we know this is wrong, right? And this is also wrong. This is false positive. This is false negative. And they are true. These are confirmed by the truth. These diamonds, they are the truth, labeled by experts. So false negative, false positive. Very good. And then we can further quantify how wrong is the location of the detected peaks. So for positive, for true positive, we evaluate the median absolute error, and then we can report final result. So these are two quantities we will use. The first one is use false negative and false positive to define F1, and the second will be the MAE. And this is the result. There are several algorithms that people use, and in this database we checked there are 4 different channels, 4 different transdermal maternal ECG channels. So we apply different algorithms, like many algorithms, to each channel, each single channel. And once we apply it to each single channel, we calculate the F1 and the MAE. And you can see that the best one is this proposed algorithm, almost. Okay, the F1 or MAE, if you compare with all the others, and this 48 citation, this is the older version of the proposed algorithm. It performs quite well. And in the traditional approach, people use PCA. And this is actually the approach used to decompose maternal ECG and fetal ECG to the separation. But this one we combine with D-shape so that you can get a better result. Okay, so it's just a summary statistics showing you that if you combine algorithms in the right way, in particular using D-shape, when you have only single channel, you can get quite good results. And all these codes, they come from this paper, so that you can find all the codes online for comparison. And this is a showcase of the result, which again we'll discuss in the second part about the decomposition. So this is the transdermal maternal ECG, and this is a decomposition. This is a maternal ECG. Okay, this is a fetal ECG. And once you get the fetal ECG by decomposition, you can further denoise this fetal ECG and get the final version. And in this final version, actually you can see something very interesting. For example, you can see arrhythmia. This is arrhythmia. So because of this capability, the algorithm itself has a potential to be applied in practice, and that is something we are talking to physicians. And hopefully we are able to really use it in practice. Okay, but this is a long journey to go. Okay, now I'll tell you some clinical application very quickly so that you know, after we spend that much effort discussing theories, developing algorithms, and finally we achieve this point, then why do we care? What can we apply? Okay, but I will not dive into all details. If you are interested in this, you are welcome to read the paper, the clinical papers. But I will tell you just the signal processing part. So the clinical paper is this one. And the focus, actually you can see is, we try to use fetus to be a radar of maternal stress. Like when a female is pregnant, sometimes they may develop some depression because of many physiological stress. And it has been well known that if the mother has some stress during pregnancy, then the children may have a higher chance to develop autism, in particular autism spectrum disease. So we want to have an early kind of understanding or early detection of the stress of the mother, so that we may be able to do some early intervention to reduce the chance of autism of the baby. So what we did was, from the transabdominal maternal ECG, we get some heart rate variability index, which I will introduce in the next slide. Then we have some experts from Germany, and they have found some females, some pregnant women with or without stress. And we simply use the heart rate variability, and we try to classify if we can identify who is in stress, who is not. Okay, and the result is at least I think it's quite convincing, because this kind of signal usually is abandoned and people do not know how to use it. But we can achieve this very nice area under curve. So it's very encouraging, I think. And this fetal stress index, which is the heart rate variability index, is actually defined in the following way, which is very simple, but mathematically it is very kind of interesting. And this is actually Juren's expertise, how to study this kind of random process. For example, I get this maternal heart rate. This is maternal heart rate called XI. Okay, you have random process. And what you do is you try to find all segments with anchors. And what does it mean by anchors? It means if the heart rate increases. If the heart rate increases, then it is an anchor point. Then you collect all segments with the increased heart rate. With increased heart rate, for example, this one is increased, this one is increased, right? This one is increased. So you collect all these segments of some width, and you collect, and you get a collection of very, very noisy and strange-looking segments of heart rate. This is how it looks like. And then what do you do? What you do is you just take average, and this is called bivariate phase rectified signal average. This is from fetal heart rate. So you get to the anchor point from maternal heart rate, and for fetal heart rate, you collect everything, and then you do the average. So you can see conditional on some dynamical behavior of a random process, okay? And you focus on, though conditional on that behavior, and you study its local dynamics behavior, which is somehow related to the covariance structure, okay? And then you can see two things. First, if a patient, if the female is not under stress, you can see it's kind of just like random. But if the fetus is, the mother is under stress, then you see there is a kind of very nice sine wave-like behavior. Okay, so what you do is you can define some kind of FSI by just evaluating the difference over two regions, which is somehow trying to quantify if there is some kind of oscillation or some dynamical behavior. Okay, so mathematically, we do not have proof yet, but it seems to suggest that we are able to use it to quantify what it means by coupling and so on. But that is open question. We are working on it. Hopefully in the future we can get something. But that is the index, okay? And we view heart rate as a random process and try to understand what's going on. Okay, another application is the Deshay to photoplethysmography. So you remember this non-contact PPG, right? You just take a camera and look at the face. And although our eyes are not that good to capture what's going on of this cheek location, okay, is there any color changes or anything? Usually it's very difficult to see, but the only thing maybe we can easily identify is if a subject is angry, then you can say, oh, his face becomes red, right? That's kind of very dramatic, extreme case. But actually, in the real life, even if right now, if you take a camera of me and you can take my face, do some facial analysis, you can actually get some information about my heart rate, even breathing. But because I'm moving freely and there is no light control, so this mission and the resolution is maybe not that high, so the mission is harder. But anyways, we have some wheel control study of a normal subject working at constant speed at 0.6 hertz. And this is how the signal looks like that you can extract from the VDD. This is short-time Fourier transform, as you can imagine. It's kind of very many curves and difficult to see which one is which. But if you run the shape, you can see two curves. Okay, the one curve is the working reason. Another curve is the heart rate. And the red one is actually the heart rate from ECG, the ground truth. So you can get the heart rate very accurate. This is a result back in 2016, which we show that actually, if you use synchro squeezing, okay, without even not using the shape, just using synchro squeezing, actually you can get quite good result compared with the traditional autoregulation. It's time varying autoregulation algorithms in various different situations. For example, when a subject is seated or standing or working, you can see that it's quite nice. And in particular, you see this is 43, this is 324. And the difference is very gigantic. And for details, you can go to the paper and see what's going on. So the possible application is the traditional heart rate variability application for sure, and disease detection or non-intrusive, non-contact physiological status monitoring. Okay, and this is about PPG for respiration detection. So here you can see this is also a PPG signal. It's oscillatory, right? But in addition to the very fast oscillation, you also see a slow oscillation. Okay, and the short-time Fourier transform looks crazy. And you can see some very interesting amplitude modulation behavior. And this is the D shape. You see two curves, 1, 2. And if I zoom in, this is 4, right? I zoom into 0 to 2. This is the heart rate. This is the respiratory rate. And here I also plot a blue curve. This blue curve is the fifth time of the this is the fifth time of the true respiratory rate, which I only want to show you that this curve, which is the heart rate, is not the multiple of the respiratory signal. So this is not up effect. We get everything correct. Okay, so you can use it in the benchmark database to estimate the respiratory rate, instantaneous respiratory rate, and so on. I think right now our result is again the state of the art. Maybe people can do better now. I didn't follow this direction I haven't followed this for 2 years, 3 years, but at least before 2021 something, during the pandemic, it was still the state of the art compared with many existing works. So, but this is our algorithm. Okay, you can get instantaneous or 60 seconds average heart rate or respiratory rate, and compare with existing algorithms. I think everything is nice. Yeah. Okay. And this is the PPG during exercise. Okay, thus we have subject runs with changing speed, and this is how the PPG signal looks like. I only show you the first 100 seconds. And if you know how to read this PPG signal, you see this is crazy, very difficult to analyze. And this is a short-time Fourier transform, many curves, and which one is which? Again, very difficult to identify. And this is the result of the shape, short-time Fourier transform. You can see several curves. The very dominant curve here is the heart rate, but there are some curves. What are they? They are the working running paths. So if we use the simultaneously recorded IMU signal, accelerometer signal, to mask them, then you can get the heart rate information precisely back. And this is the summary statistics. Again, I think the result so far is again the best compared with all the others. Good. So it can somehow helps you to get more accurate heart rate variability analysis, but we will not go deep into heart rate variability analysis, so this may not be a big concern. But just remember that the more accurate you can calculate heart rate, the more accurate you can get heart rate variability analysis. I think this is the last application. It is about cadence analysis or accelerometer analysis, and this is the published paper. I think it's published in last year. Right now it's last year already. Right now it's 2024. It was published in 2023. The basic idea is very simple. Again, just like I told you, in practice, actually the oscillation is always non-stationary. Non-sinusoidal, and this is the signal we get from the device, either this tip track device or from watch. There is always this accelerometer sensor which records your motion information, and this is how the motion information looks like when a subject is working, when the sampling rate is high enough. Many devices nowadays, their accelerometer sampling rate is not very high, but if the sampling rate is high enough, for example 50 Hertz, then you can see a very beautiful reason. And in this reason, you can see that from time to time, it's certainly non-sinusoidal, and from time to time they are different. And this is the signal, zoom-in signal, and if you take a look at the synchro squeezing, short time Fourier transform or synchro squeezing, you can see there are several curves, right? And those curves, sometimes you see the fundamental frequency is strong here in the beginning, becomes weak later. Strong, weak, right? So it tells you that, well, the morphologies cannot be fixed, and then will be the topic we will come back in a bit to discuss what's going on if the working pattern is not fixed. And this is an illustration of the D-shape, which helps us to do a further analysis. So this is a subject, this is the IMU signal when a subject is working, which is upstairs, downstairs, upstairs, and work on a flat floor and repeat. And this is the short-time Fourier transform spectrogram, and this is a D-shape. You can see the D-shape gives you a very beautiful pattern of the working frequency and so on. And this is from the work from this Indiana University working and the driving study database, which you can find online easily. And there are several questions we can ask using D-shape. The first one is we want to ask if a subject is working from using the IMU installed on the wrist on your watch, for example. And this is the result. Actually, if you use synchro squeezing, okay, to define some features which we haven't discussed, but the result is very simple. Just determine accumulate the energy over the harmonics, then you can get a very high accuracy. Okay, and the entropy is also good, but it is slightly worse. You can combine both, but the result is okay. And there are several other existing indices that you can use to detect working, but their performance are not very good. In particular, when IMU is installed on the wrist, and this is the F1. Overall, using synchro squeezing features is quite good. The second question will be, can we determine the cadence? The answer is yes, we can. And this is the result. You can see that the result you get from the IMU sensors installed on different locations of the body, left ankle, right ankle, hip, and they are the standard locations and nice locations. They look very similar. And if you do the wrist, because wrist, your hand may have another layer of free movement, so it is less easy to get a good result. But you can still see there is a very, very, very nice trend. About this is 1.98, 1.96, 2.6. What does it mean? It means that when you are working on a flat floor, your speed is constant. It's kind of in the middle, but when you are climbing up, the cadence is slower. But if you are downstairs, the speed is faster. The speed is faster, and there will be some technical details about cadence or stride that you can see in this plot, which just show you that the gait analysis is actually a very complicated topic. And this is agreement among different sensors from different locations, because usually you don't want to say, I want to install this physical activity sensor in your hip or in your ankle or something. That's very inconvenient. You want to just wear a watch. But when you wear a watch, you get a lot of freedom. So you want to study, okay, what will be different? For example, wrist and hip, wrist and ankle, wrist and ankle. You can see if you use this V-shape algorithm, actually all have quite good agreement rate. And this is the BA plot, okay? And the future work will be, can we use this wave-shaped function idea to further study physical activity or to gait analysis? The answer is yes, we can. And actually, in physical activity society, there have been many people using this signal to do analysis. And the idea is very similar, so the combination is very possible. So that will be the future work. There are several other potential applications, for example, in music, but I don't know too much about it. I just showcase you some results, or do biology analysis, for example, counting wolves by holding. You can see that short-time Fourier transform is very complicated, the shape, and you can use the shape patterns to do the counting and so on. So it has several possible potential applications. We will do it in the future, and that is for this session. Thank you.